Okay, so any doubt from the last class or last session? No, like what we discussed the problem last time. Yeah, torsion problem. Yes, yes. Okay, okay. You were able to understand. No? Okay, okay. Thank you. Ah, okay, okay, okay. Yeah, yeah. Okay, okay. Ah, okay, okay. Yeah, 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 yeah. Yeah, I think that might be given to showcase that we are not putting the strain gauge near to the ends where the twisting moment is applied, because we have this infinite principle. So we don't generally measure quantity near to the ends. We measure it some. Yeah. So maybe because of that, to make sure that the position of strain gauge is far away from the ends, that was given. Maybe. Yeah. Yeah. Ah. Okay, okay. Yeah, 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 yeah. Okay, so we'll start today's session. So good evening all. So welcome all to all of you for the today's eighth session, and today's topic is bending of beams. So in the previous week lecture, professor has discussed about the bending subjected to beam subjected to pure bending moment. So that is pure bending. Okay, so we have seen the derivation of the bending equation there. Okay, so that we'll be using today, and we'll solve some problems from that, and then you understand that why each concepts or why each assumption whichever is being taken in the development of Bernoulli beam theory, so why it is there and what it means, like what it gives you at the end. So why the symmetry plane is required, then why we call say the material is isotropic, how it will easier our life. Okay, so those sort of things were discussed in the lecture, and then in the second lecture it was discussed about the beam where you have variation of the bending moment also. So what we do when there is a variation of the bending moment. So for pure bending, as you know, shear stress will be zero, shear force will be zero basically, and the only bending moment will be there, and that will be constant over the length of the beam. But what happens in case of a cantilever beam or 3 point bend test or 3 point bending beam? So there will be a variation in the bending moment also. So then how we utilize the same Euler-Bernoulli equation to solve those problems? And basically these are called strength of material solutions of beams. Okay, so there is something else which also professor discussed, was known as elasticity solution. Okay, so that is the different thing is elasticity solution. So that also professor discussed in the lecture, and then he showed how the photoelasticity can be used to uh, find the stresses or the variations. So you can see the photoelastic fringes. Either you bend it, beam, simply supported beam with constant movement, so you will see the fringes, as well as if you push a beam with their finger, a cantilever beam, so there will be a different pattern of the fringes. So that shows that as the condition changes, as the variation of the bending moment and the shear force changes, the fringes also change. So they give you a fair idea, like how uh, they are different than that. So you can visualize the things using the fringes. Okay, so that is there. So we'll do some problems. So basically in this we have certain, in a sense, that two problems we can say. That one is like where we have been given the dimensions of the beam of some these kind of cases. The dimensions will be given, and then we asked to find the maximum stress, or what is the maximum moment, something like this. A moment may be given, then stress will be found. So those are analysis type of problems. So you have to use the bending equation or the Euler-Bernoulli beam equation, and you have to find the quantity which have been asked. That is one way. Another way is to basically the design. So in that case, the moment may be given, mostly moment, as well as the allowable stress would be given. So what is the allowable bending stress that the body can be subjected, or the beam can be subjected, and based on that you decide upon a dimension of the beam. Okay, so basically in the books also many questions are there which are very monotonous, because the same kind of questions are being asked for many this thing, so for very long. So I have chosen some different type of questions. I tried my best from my side, so that they should not be monotonous kind of. So we should be able to have a different perspective, that where else we can use the same theory. Okay, so so that they will be a little bit more intuitive, I feel. So it will give a broader idea that the same bending theories, or the Bernoulli beam theory, we can use at different situations. Okay, and all the situation, it will be a case of bending only. It's not like I'm dealing with another phenomena. The phenomena always remains the bending. The way the beam is being bending will maybe a little bit different. Okay, and I hope that also in some of the good textbooks or reference books you can find more such problems. Okay. Okay, so we'll start today's session. So we'll first do some analysis problem, and then we'll do the design problem also. Okay. Okay, so let's come to our first problem. So this is the first problem. So here it is given that a high strength steel wire of diameter D is bent around a cylindrical drum of radius R0. So you can see that there is a cylindrical drum. This is a drum. So the cross section only is being shown. Okay, it is there is a length of that drum, but around that drum there is a high strength steel wire, this one, of diameter small d, and it is being bent around that drum. Okay, now using this, it is asking us to determine the bending moment M and the maximum bending stress in the wire, assuming that these are the values given to us. Okay, so the diameter is given, as I told. So it's an analysis problem, because already the dimension is given to you, and you know what is being bent here. The wire, steel wire, is being bent here. Okay, so it is this part is kind of the curvature of the bent wire. Okay, this is forming the curvature, this is where it is bending. So now it has been asked that it has been already given that the diameter is given, this radius of the cylinder also is given, the Young's modulus is given. So it has been asked what is the moment and what is the maximum bending stress for this case. Okay, so we'll try to solve first this. So this is an analysis problem, so that's why I'll try to make you understand that what is the difference between the two, because like design problem, you are specifying a value for the diameter or whatever. Okay, So there you specify a specific value inside. Okay, so let's solve this. Okay, so let's write down whatever is given to us. So first the diameter of the wire is given, so it is 4 mm. Okay, and then the radius of the drum is given. I think that is 0.5 meters, 0.5 meters, and the Young's modulus is given as 2 into 10 power 5 MPa. Okay, so these quantities are given. So I'll do what, I'll copy this figure and we can discuss it in detail. So we have to see that how the bending is happening here and how we can relate it with the way we have studied in the lecture. Okay, so if you see, this wire is going over this drum. Okay, this wire is going over this drum, and this drum is causing it to have a curvature. The surface of the drum, which is here at a distance r0 from the center, it is kind of causing it to have a curvature. Okay, so, and obviously there will be some force will be there in this wire, because you know what bending cause. Bending, when I talk about pure bending without shear force, where the bending moment is constant over the length. So in case of pure bending, you have seen in the lecture that shear stresses are absent. Gamma xy, gamma xz, those are absent. Okay, there is a 0. And we have seen that sigma y, sigma z, or sigma yy, or sigma zz are also absent. So only sigma x is there. That means there is an axial force. So in a similar sense, if there will be an axial force in this wire, that will cause this part to bend. Okay, if there will be an axial force. So this you have to think through yourself that how it is bending. So obviously there is an axial force which will cause this wire to go around this surface of the drum, and hence this portion will be under the bending. Okay, so now as you have seen this, so let's understand that this part of the drum which is in contact with the wire is making the wire to undergo the bending. Okay, now if we see, so the wire is being bent about a point. Okay, and what is that point? This is that point. That means this is becoming the radius of curvature. This one is becoming the radius of curvature, but not till the surface. As you know, the radius of curvature, as you have seen in the lecture, is still the axis of the neutral axis. So I'll draw for the reference case. So you might have remember, so professor has taken some section like this in the lecture. So there was not like this. Something like this. So this was the neutral axis, and he has given something like this. This was the phi. Okay, and the radius of curvature was measured till the neutral axis. This was measured as rho till the neutral axis. Okay, the neutral axis is axis with no stress. There is no stretch happening. There is no strain on this axis. This axis doesn't extend or compress. This axis remains of same length. So that means the definition of the radius of curvature is still the neutral axis. So the same way we have to follow in our example also. Okay, that means here also from this center the radius of curvature will be till the center of this wire. Okay, and you know it's a wire, so wire will be circular in cross section. Also is given in the problem, it's a circular cross section wire. So from this we can directly write the expression for the radius of curvature. Okay, so this will be our radius of curvature. Radius of curvature. So radius of curvature will be r naught plus d by 2. Okay, half of that will be the radius, so half of the diameter. Okay, so this will be the radius of curvature. Okay, so now we have utilized whatever we have been given to us. Now let's go proceed forward and see what we can do with this using the bending formula or the Euler-Bernoulli beam theory, which we have derived the formula from that theory. Okay, so what we know that bending formula. So bending formula. So what is given that we know that mg or mb, I will say mb by iz is equals to minus of sigma x upon y is equals to E by rho. Okay, so this has been the formula. Okay, and y minus is there, as you understand that, because the positive sign is taken, this word upward is a positive sign. So for a positive bending or positive bending moment, there will be compression in the above layer and tension in below the neutral axis. So to make sure that only that negative sign is being ensured, because if you take positive y, it will remain, y is positive, so this will remain negative. That means it shows that it is a compressive stress, and if you go down, your y will be negative and it will become, the sign will vanish and it will be a tensile stress. Okay, so this is the bending formula. Now we have been asked two things in the question, so let's go one more time to check what we have been asked. So we have been asked to determine the bending moment m and the maximum bending stress. Okay, so we have been asked to find the bending moment and the maximum bending stress. Okay, so let's do that. So what we need to find, bending moment, so that is our mb that we have to find. Okay, and second is maximum bending stress, that is sigma max. Okay, so if you see, if you want to find the bending moment, so what we have to, what has been given in the formula, this has been given to us, we know this part. Okay, what has not been given, that is mb if you want to find, and we need to know what is iz. Okay, so that means we should find mb and we can find iz, that's not an issue, and we know this part. So what I will do, I will write these two only first. Okay, so I will say mb by iz is equals to E by rho. Okay, E by rho. Now first let's find iz. Okay, so iz of what we will find iz of the portion which is bending. Okay, so here the wire is bending, so we have to find the iz of wire. Okay, so wire is a circular wire, so it's have a circular cross section like this. Okay, so we have to find about this axis. Okay, so this axis we have to find. So what will be the iz about this axis? Iz will be pi by 64 d to power 4. Correct? That will be the iz. So now we know iz in the above formula. Okay, let's put it there and solve for it. So our mb will be E into iz by rho. Okay, so E is given to us 2 into 10 power 5 MPa. Okay, and iz is given by pi by 64 into d to power 4. So what is d for us here? It is the diameter of the wire, that is given 4, so 4 to the power 4 divided by rho. So we have just found rho, so rho is here r naught plus d by 2. So what I will do, I'll put everything in mm. Okay, so r naught is 5.5 meter, so 500 mm, and plus d by 2, so it will be 502 mm. So it will be 502. Okay, so I request any one of you to just find what value it gives to us. Yeah, 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 yeah. Yeah, pi by 64 t to the power 4. Yeah, yeah, it's yeah, yeah. It is different. So suppose this is z axis. Suppose uh, this is y axis. So what we do is, that is the x axis. This is the polar axis. The x-axis here. The axis in the longitudinal direction. That is the polar axis. So you know that I x-axis is what? I y plus I z. And if you have I y, and you know I y and I z are same. They are same because it's a symmetrical shape circle. So if you add these two, it will become pi by 32 d to the power 4. That is the I x-axis, and I x-axis is called the polar. Okay, so I x-axis is the polar moment of inertia. Okay, that is I x-axis. So I x-axis is along the is along the longitudinal direction. Okay, I y and I z is on the cross section. It's on a plane, on a cross section, on the circular section. But I x axis is on the longitudinal. So that is which we use in the torsion formula, because what we are doing, we have a length of a circular some shaft, and we are twisting it. Okay, so there we use IZ, but here we will use IZZ, and that is for the bending. Okay, yeah, yeah. So we'll use that here. So let's see what comes from this expression. If anyone can evaluate this for me, this expression. We have used NPA here. $5007. Okay, 5007. Okay. Yeah, this will be Newton millimeter, correct. Okay, this will be Newton millimeter, because everything is millimeter and MPa. So it will be Newton millimeter. So what we can say, it is 5 Newton meter, correct. So that will be, yeah, so that will be the bending moment, 5 Newton meter. Fine. Okay, so that we know the bending moment. So if the radius of curvature is given to us, and the elastic property, that the Young's modulus is given to us, so we can tell what is the bending moment. That is one part. Okay, now coming to the another part of the problem, where we need to find the maximum bending stress. Okay, the maximum bending stress. So as you can see, obviously when this is bending, so I will do what, I will draw a very enlarged figure of the steel wire, okay, so that you can understand. So if you see, suppose it is something like this. Sorry. Suppose it is something like this. I am trying to draw as much as possible correctly. Okay, consider this is not changing the like thickness. Okay, thickness is same. Here it is got changed, but it is same. Okay, assume that it is same. Okay, so it is same actually. So I am saying that suppose from this end to this end it is in curvature, okay, in contact with the uh, cylindrical drum, okay, and this part only is being in pure bending, okay. So what I told, that there will be a neutral axis, okay. So let's draw the neutral axis. Suppose this is the neutral axis, okay, this is the neutral axis, okay. And as you know, so here the material is what? So here material is isotropic, it is given, okay. If nothing is being specified, we can easily assume that it is isotropic, and also E is given 210 for 5 MPa, so we can go with that assumption. So obviously from this neutral axis, you know that the maximum will be on this surface and this surface, okay. The maximum stress will be in this surface and this surface. But from this figure, can you judge what is the nature of the bending, whether it is causing sagging or hogging, whether it is a positive bending moment or negative bending moment? Can you see? Can you guess what is the nature of the bending from this figure? Negative, okay, correct, very good. So it is negative, actually it is hogging. So what it is causing? It is causing a tension on the upper surface of the wire and a compression on the below surface of the wire, okay. So as you know, on the neutral axis, this red line represents a neutral axis. So this red line is neutral axis, okay. So as you know, on the neutral axis, no stress develops, no strain is there, okay. Stress, strain are zero, okay. But what happens away from the neutral axis? You know, because the strain varies linearly, okay. We know that strain varies linearly with y. So when strain varies linearly with y, obviously because of the Hooke's law, where we are using a linear constitutive relation, Hooke's law. So because of the Hooke's law, stress also varies linearly, okay. So this surface also will be in tension with same stress as this surface, which will be in compression, okay. So basically the upper surface as well as the below surface of the wire will be subjected to stresses. One surface will be in tension and another one will be in compression, okay. So we need to find the maximum. So obviously the maximum will be at this surface only. We need to find the maximum stress, okay. So our objective is to find maximum stress. Find maximum stress. Maximum normal stress or bending stress, basically we call here maximum bending stress, okay, because this stress is developed due to bending. So we need to just find either on this or this surface, okay. We are more interested in the maximum, okay. So what I can do, using the same bending formula, so here I'll get the maximum value, so I can use these two terms to find the value of the maximum stress, okay. So let's find that. So we know that I'll drop the sign now. Why I am dropping the sign? Because now I am interested in maximum, and maximum is same in the maximum value, as I am now interested in value, not in the magnitude, in the thing that whether it is compressive or tensile, okay. My objective right now is the value, so I'll drop the sign and I'll say sigma max by y, which will be equal to E by rho, okay. Okay, so let's find sigma max, and I told where maximum will occur. So maximum bending stress will occur at the surface of wire, okay. So you can choose either of, okay, the tensile surface or the compressive surface. So sigma max will be E is 2 into 10 to the power 5, and y will become d by 2, okay. So it will be d by 2, d is 4, so it will be 2 divided by rho. So rho is what? 500 plus 2, okay. Yeah, so it will be sigma max will be 2 into 10 to the power 5 into 2 divided by 502. So if you can solve this one, what you will get? It will be 2 into 10 to the power 5 by 251, I think. Yeah. So can you divide this and find what will be the answer? final answer? .8 MP. Okay, so I'll say 797 MP. So that will be the maximum stress, 797 or 796.8. Okay, and it will occur on the surface of the wire, and this is due to bending. Okay, understood? So this is the stress generated due to bending. Okay, so that's how we can study a problem, something like this. So this is very common. Like if you ask me what is the situation where these kind of things will happen, so where, yeah, yeah, no, why is the distance? Okay, I'll represent. Why is this? It is the distance from the neutral axis where we are finding. That is why. Okay, it is the distance from the neutral axis to the surface where we want to find the maximum, where we want to find the stress, basically bending stress. It depends on us. So now our objective was to find the maximum value. So we took y is equals to d by 2 because we want to find at the surface. Okay, basically. Yeah, come again. Yes, Arjun. Yeah. 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 Yes, it will pass through. It is the longitudinal axis also. Yeah. Okay, what I'll do, I'll draw the longitudinally wire as well as in the cross section. So suppose this is your wire and this is your longitudinal axis, and I'm drawing here the cross section. This is the cross section. Okay, so it also passes through here. Okay, so basically this is your neutral axis, this which will pass through the center. This will pass through the center of the circle, and what we are doing, we are trying to find, this is our y, because we are trying to find at this point, at this top point here, we are trying to find the stress here, because you are correctly saying because the stress will be 0 along this axis, there will be no stress. Okay. Yeah, Lokesh. Yeah, if you take downward, it will be negative, and accordingly the thing will change, and the magnitude will be same. Only one time it will be tensile, one time it will be compressive. Yeah, that's all. It can, we can take it negative. Okay, so this is our y, this distance from the centroid, from the centroid to this place, point, red point marked, this is the y, because we, as we discussed, either the stress will be maximum here or there only. Okay, so anyway, any point we can choose, because our objective is now to see what is the maximum value. Okay, we already know that at one surface it will be tensile and another surface will be compressive, and from the nature of the bending we know on this surface it will be tensile, okay, by nature of this bending case, and we know here it will be compressive. Okay, so that knowledge we have, just we need to find the maximum value. What is the maximum value? Obviously it will occur at these surfaces only, so I have chosen accordingly that point, and the distance of that point from the neutral axis is known as this y. This y is nothing but distance of the point where I want to find the bending stress from the neutral axis. That is that means that is the meaning of this y. Yeah. Okay, so this is how we'll find that what is the sigma max, and we already know that at one surface sigma max will be tensile and another surface it will be compressive, and you can see that the values are very high. If you compare with what we studied in mild steel, so it was around 250 MPa was the yield, but here it is very high. So actually because it's a high strength steel wire. Okay, so basically high strength steel wires are very having a very high yield stress. So their yield value will range between 1100 or 1200 to around 1500 or even 1600. And these are basically wires. These are not single wire. There are strands of wire. So basically those wires which are used in the pre-tensioning and post-tensioning, those are one of the examples. So of the high strength steel wires which I can quote. So what I was saying, that where we can find the applications, like what kind of situation we will see in real structures, if I say. Okay, so the best I could say, like above the pulley. So this could be the pulley and the wire going above it. So because what we know, the steel wire which we use over the pulley is also subjected to uniaxial loading. So it will be uniaxial till here, but as soon as it enters this, so it is kind of bending because of this pulley. Okay, so one way this, but we have to think like we have to put a proper idealization there about the shear, whether whether there is a friction between the pulley and the wire or not. Okay, because if the friction is there, that friction will cause some shear. Okay, so that is there one example. Then there are on these bridges we use wires. Okay, so bridges also we can have these kind of structures which will pass over the wire from one side to the another side. So there, so best example we can see of pulley. Okay, yeah, so that is this one. So in this problem we came to know how we can analyze or how we can find the moment, bending moment, as well as the value of maximum stresses if we know the dimensions already. As in this problem we knew the dimensions, so we would able to find the other values. Okay, okay, so I hope you understood this part. Okay, so we'll move to the next problem. Okay, yeah, 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 yes, yeah, 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 for a linear constitutive relation. Yes, if your material model, which is that we are using here Hooke's law, so for Hooke's law it will be like that. But if the constitutive relation you change, you bring up some different material, some orthotropic or anisotropic material, so the variation of the stress may not be linear. Okay, although the strain variation will remain linear. As you may remember, also in the lecture professor told you that the variation of the strain which they got epsilon x, they got that was minus y by rho. As you remember, epsilon x was minus y by rho or minus y into d phi by ds. So that variation they got irrespective of the material. Okay, there is no involvement of material there. So what we learn from that, the variation of the strain will always be linear in homogeneous beams. Okay, or homogeneous isotropic beams. But when you have a constitutive relation which may be non-linear, means the stress and strain are not related in a linear fashion, then the variation of the stress could not be linear. It could be non-linear also. It could vary as a y square or something like that. But in this case, because we are living in a very idealized situation, so our situation is we are using isotropic Hooke's law. Hooke's law is linear. Sigma x-axis, we know how it's related to epsilon x-axis. So it's a linear relation. So that's why always the variation of strain will be linear, that will be there, but the variation of stress also will be linear. That is the catch. Yeah. 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 Uh, so what sir told there, yeah. So what happens if you have shear stress also involved? So let's take up an example of that. Okay, then we'll move to next problem. So let's say we have some situation like this. We have a beam, something like this. Okay, uh, some beam like this. We have roller here and hinge here, roller here, and I have a point load P. Okay, and this length has L. Some. Okay, so what I'll do, I'll draw the bending moment diagram and shear force diagram of this beam. So let's do that. So first I draw the shear force diagram. So you know it will be something like this, and vertical here, and then it will be like this. And if I draw the bending moment diagram, so bending moment diagram will be something like this. Okay, so this will be PL by 2, and it will be minus PL minus P by 2, sorry, minus P by 2 here, P by 2 there. Fine. So this will be our shear force diagram, this will be our BMD. Okay, so now you see that there is a variation. Now the bending moment is varying along the length. From this portion to this portion it is varying, it is not constant. Okay, and you can see that there is a shear, there is a positive shear here, there is a negative shear here. So what is happening, because and you have found that if you remember the lecture, dm by dx comes as minus v. This was done in the last lecture. Okay, dm by dx comes as a minus v. That means whenever there will be a variation of m, that is the bending moment, whenever there will be a variation of the bending moment, there will be always a shear force associated. Okay, that means as soon as you come up with a case where you are finding a variation of bending moment, invariably you will come up with a shear force also. Now the bending theory which we have just shown the formula we have used just now, that is developed only for pure bending, and it will give an exact answer only when the body is isotropic and it is subjected to pure bending and it is a slender beam. Those are the very basic foundational, I will say, assumption requirements. The beam should be slender, that means the depth of the beam should be far less than the length of the beam, first. Second, that it should be isotropic material. Okay, and the third, it should be subjected only to pure bending. In that scenario only, whatever formula we just saw will give us an exact analysis. Now what happens in this scenario where we don't have pure bending? Okay, we have a slender beam, we have isotropic, I am saying that is still true, but we don't have pure bending. So you can see the bending moment is varying, and there is also involvement of shear stress. As you know, in pure bending shear stress is 0. That means here we can't get an exact value from by using just the bending formula. Okay, here the exact value we can't find using the bending formula. That means it will be somewhat approximate, and that's what is called the engineering analysis. Okay, that is the engineering analysis where we are making an idealization. We are saying, okay, this shear is happening, I know, but let's forget about it and let's focus on the bending moment itself. Let's do the design or let's do the analysis based on that, and just forget the shear force for right now. And you will find that later on, you will find when you will go to the deflection, you will find why he has done that. Most probably, I am sure you will find when you will go to deflection that why he did. And in the coming lecture, first of all, we will go through the shear stress, how the shear stress vary along the depth of the cross section, and then even after that, when we will go to the reflection, what we can do, we can find that how much this shear force is causing deflection. So you will find that the deflection caused by shear force in case of slender beams is about 5%. Means if suppose total deflection is 100%, out of that only 5% is caused by I am saying a rough figure, 5%, it varies between 1 to 5%. So you will find that it will be only 5, this shear force will only contribute around 5% in the deflection, and rest of the 95% will be contributed by the bending moment. So that is why we are doing this engineering analysis. That is why we are allowing ourselves to do that. Otherwise, it would be a wrong if it would not be the case. So, although that part will come a little later in the lecture, but I am revealing to you. Okay. So why we are saying it is okay, although it could not be, but it is okay, because engineering is all about the approximations. Okay. We don't go necessarily most of the time for the exact value. We most of the time we hang around with the approximation, and they should be good approximation. So that is what we will do here. So yeah, in this case, now coming to your question, you said that the variation, but no, we will never say the variation is still will be linear. The variation of the stress will be linear, but the problem is what? So I'll draw some sections. I hope I am making some sense to you guys. So what I'll draw some sections. So I'll call 1 1, 2 2, 3 3, 4 4. Okay, I'll do till 4 4 because the other ones are exactly same as that, the left side. What I will do, I'll draw the variation of the stress along the depth. Okay, depth, you know, this is the depth. Okay, cross section I'll draw something like this. So I'll blow up that figure so that you can understand. So first I'll do cross section. Okay, so this is the neutral axis, suppose neutral axis. Now what I will do, I will draw the variation for all the cases. First I will draw 1 1. So section 1 1, I will draw 2 more lines. I will just extend this line, and I will extend this line also. Okay, so for the sake of sorry, yeah, now I will draw variation. First is 1 1. So 1 1, as you know, what will be the bending moment of 1 1? Bending moment of 1 1 will be less compared to 4 4. Okay, so we know what is the equation. We know mb by iz is equals to minus sigma x by y, that we know. Okay, and I am drawing the variation along the depth. So what I will do, I will vary, I will write this sigma x is equals to minus mb into y by iz. Okay, now mb I will write for first section, no, for this section. So I will write the formula also. So for first section it will be sigma x will be minus mb into m1. I will write m1. It will be now m1 into y by iz. Okay, now m1 is constant, iz is constant, only variation is of y. So y will vary, and it will vary from 0 and from positive something. So I will say this is h here, and this is minus, I will say, yeah, this is plus h, this is minus h. Okay, and it is subjected to positive bending. Okay, it is subjected to positive bending. That means the bottom portion will experience tension and the top portion will experience compression. Okay, so what I will do, I will draw it. I'll draw the variation. Okay, so how it will be? It will be somewhat like this. Okay, and this will be in compression, and this will be in tension. Okay, now I'll go to section 2 section 2 What will be the for section 2 again a straight line. Now for section 2 I will write again the equation. So equation will be sigma x is equals to what? M minus m2 y by iz. Now the only thing has changed, which it is m2, rest is same. Okay, and you know that m2 is greater than m1, and it is not changing at section 2. Section 2 m2 will remain this value. This will be the value of m2, this bending moment at section 2, and that is greater than m2, that m1. That means this sigma which is at x1, I will also mention x1 x2. So that means sigma x2 will be greater than sigma x1, and I am saying for the whole variation. Okay, although it will be 0 at the neutral axis, rest it will be more. So how I have to draw? I have to draw a bigger thing. Okay, I will take a bigger point. So I have to draw something like this. It will be more. Okay, so you can see sigma x2 is more than sigma x1 at the corresponding points of y, at the corresponding levels of y, it will be more. Now let's go for 3 3. Let's go for 3 3. Okay, so I'll draw a vertical line for 3, and now what will be the formula? Sigma x3 is what? Minus m3 y by iz. Again, you know what is changed? M3. Rest all are same. That means sigma x3 will be more than sigma x2. That means what will be the variation? It will be more, something like this, more than x2. It should be more than that, and but it will be always compression above, tension below. And let's go for the final section, which is the section where we are having maximum bending moment. As you can see from the figure, section 4.4 is having the maximum bending moment. Okay, so now we will draw for that point, which is section 4.4. Okay, so this is section 4.4. So what will be the value here? Sigma x4 will be minus of m4 y by I z, and we know that m4 is the maximum of all. Okay, so nothing is more than the moment at that point. So I'll draw it the maximum one. So something, this will be the maximum. Okay, so this compression and here tension. So that's how from section to section. Now you can visualize how from section to section the bending stresses will change, and where now if somebody asks where the maximum bending stress will occur, so now you have to, from this experiment or this figure, now we can always say that if we want to find where the maximum bending stress will occur, we have to find first of all if the bending moment is not constant. If the bending moment is not constant, I'm saying if the bending moment is constant, all these values, all this top value will be same, they won't vary. That is the point, whole point. Okay, but if the bending moment itself is varying, like we can see here, the bending moment is varying, the point or the section where we find the maximum value of the bending moment, that point will only be the place where the maximum bending stress will occur, and that too on the top fiber. Either you work with the top fiber or you go for the bottom fiber, but that only. So either this place or this place on the section where you are having maximum bending moment. That is the point. But you can see the variation of the bending moment will not be nonlinear in this case also, because we have said the material is isotropic and we are using Hooke's law. Fine? Yeah, it will be linear. Yeah, it will be linear, but it will change from section to section. Okay, it won't remain same. Yeah. 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 Okay. Yeah. 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 Yeah, so okay. See, for bending moment, how we do. So I would suggest once that you go through that engineering mechanics also, that lecture. But I'll explain here that what we do. We have done this on the first class also. What we do, we cut the section. Okay, we cut the section, we release the force. So we know that there is a reaction coming here. Okay, from at this, if we cut the section, and what is the distance? Suppose x is the distance, and what is the reaction? We know the reaction in this case will be p by 2. Okay. So what is the moment at this section? It will be p by 2 multiplied with this distance x, that is p by 2 into x. This is the bending moment at this section. Now we see how it is going. So if you see, this p by 2 into x will cause it to positive bending moment. It is causing it to sag, not hog. Okay, that is why it is taken as positive. Okay, because it is going to clockwise. because if we look on the left hand side of the section, clockwise will be positive. If you look on the right hand side of the section, anti-clockwise will be positive. So suppose if this here the reaction, instead of coming this way, if the reaction would have come this way, and at this section this would have been this way, which means anti-clockwise, then it would have been negative. So on the left hand of the section, a clockwise movement is positive. On the right hand of the section, anti-clockwise movement is positive. Correct? Okay. So yeah, from the reaction we have to look in that from the reaction perspective. Yes. Okay. Yeah. So this is the thing. So I'm glad that we had this discussion, because many times we're not able to understand like what is happening at each section. So when a variation comes, so we think now how to handle this problem. Oh, there is a variation in the bending moment. Okay, so it's good that we had this discussion, because now it will clarify things like how to approach the problem where there is a variation in the bending moment. Okay, although we apply the same bending theory, and later on you will understand why. I am pretty sure professor will explain this by the example of, I think, for deflection, because that is the most important part there. So from there he will explain how we are still using the bending theory, and although there is a shear force. Okay. So let's move to another question. Okay, so what is this next question? Says that a vertical post of 2.5 meter in height must support a lateral load of 12 kilonewton at its upper end. Okay, so you can see there are two vertical posts. One is this made of wood. Okay, this is a wooden vertical post. Another is of some material like aluminium, and it is a tubular, means it doesn't have a it's a hollow. Okay, it's not solid. Okay, so it is also, both of them are subjected to same load P at the end. Okay, and this base you can see is fixed. Okay, there is no displacement or deflection happening here, or rotation. Okay, that means you can consider this as a cantilever. Okay, because their load has been applied normal to the axis, so it acts as a beam. Okay, and in this end is totally fixed, that means it's a cantilever. So now two plans are proposed: a solid wooden post, so this is a wooden post, and a hollow aluminium post. Okay, now what is the minimum diameter d1 of the wood post if the allowable bending stress in wood is 15 MPa? Okay, now it is asking you to find the diameter. Okay, subject to the condition that the allowable maximum allowable bending stress is given for the wooden case. And the next is with what is the minimum required outer diameter d2, this one, of the aluminium tube, this tube, if its wall thickness is to be 1/8 of the outer diameter. So the thickness of the wall is 1/8 of the outer diameter, and the allowable bending stress in aluminium is 50 MPa. Okay, the allowable bending stress in the aluminium is 50 MPa. So it is kind of a design question, because here we have to prescribe the value of the diameter to design it. Okay, so let's we'll do this one. Okay, so first we'll do the first part. So yeah, so our load is, so what I will do, I'll directly write the bending moment. So you know it acts as a cantilever. So this is the fixed end, this is the free end, and there is a load acting at the free end. So if I want to find, if I draw the bending moment diagram of this, so you know how the bending moment diagram will be. It will be linearly varying, something like this. It will be 0 here, and it will have a maximum value at the base. Okay, and this will be P into that H distance. P is the load, H is the distance. So I will directly write what is the bending moment. P is given as 12. So P into H will be the bending moment. So P is given 12 and H is 2.5. So it will be kilonewton meter in kilonewton meter. Okay, so I think this will come 30. Yeah, 30 kilonewton meter. Okay, So we got the bending moment for the wooden case. We are solving the first wooden case. Okay, now let's write down what is the allowable. So the allowable stress for this is 15 MPa. Okay, so bending stress, so sigma allowable, and that for wooden case, wood is 15 MPa. That is the allowable stress. Okay, now let's go to the bending formula. So our bending equation. So what we know that MB by IZ is equals to minus sigma x upon y is equals to E by rho. Okay, that will be the value, that will be our equation. Now we want to find the diameter. Okay, so has been given as d1 in this case, so let's the diameter is d1. Let the diameter is d1, which is already given. Now we know what is the bending stress, what is the bending moment. We have found the bending moment, we know this. We know what is the allowable bending stress, so we know allowable value. What we don't know, that we don't know where what is the diameter for which we should design, so that it will have this allowable value, and also it will be able to resist this moment which is this given. Okay, so basically we have to design the diameter. So what I will do, I will draw the cross section. So the cross section will be something like this. Okay, this will be ZZ axis. Okay, I am drawing the cross section of the post. Okay, and this will be the center. Okay, so as we have discussed, where the maximum will occur, the maximum will occur at the this topmost point. Okay, if it is bending, or if I mark in the figure, so you can see it is bending, so some bending moment will be acting something like this. Okay, so something like this. So if we see, so the axis of bending, it will bend around this axis. Okay, so either the maximum will be here or here, but one place it will be tension, another place it will be compression. I'll change the color to marking, so either here or it will be here. Okay, so as per that case, so I have rotated the cross section here, don't get confused. So either it will be there or here. I've just rotated that cross section for the ease of looking. Okay, and the movement is acting like that only. So there also I have shown how movement is acting. You can see the movement is acting. This is our ZZ axis. Suppose the movement is acting like this. So I will represent same movement here. So it will be like this. This is the movement acting. Okay. So for this case, we know how to find IZ. IZ is what? Pi by 64, and d1 is the diameter, so d1 to the power 4. And what will be the y? Y will be what? d1 by 2. It will be half. That is the radius where we are going to find the maximum value. Okay. So what I will do, I will insert these values here. So our moment is 30 kilonewton meter. So 30. I'll convert everything in meter, Newton and mm. So it will be 10 to power 6. It will get converted into Newton mm. Okay, words in kilonewton meter, divided by what our IP, the IZ, that is pi by 64 into T1 to the power 4 will be equal to, I will drop the sign because what I am doing, I am going for the maximum value, so no need of sign here. Okay, so it will be 15, that is given to us, maximum allowable value 15, and that is in MPa. So MPa is also Newton per square mm, and that will be divided by d1 by 2. Okay, so from here we can get it directly that 30 into 10 to the power 6 divided by 15 is pi by 32 d1 cube. So it is d1 cube is equals to, or I will write d1 is equals to 2 into 10 to the power 6 into 32 by pi cube root. So if someone can help me to find this value, 2 into 10 power 6 into 32 by pi cube root of that. So what it will give? Okay. I think that is coming closely correct. 273.1. So I'll restrict it to 273. I'll say 273. Okay. So that will be the diameter D1. Correct? 273. Okay. So we found the diameter for which diameter, that is 273 mm, for which the lamp post or that post which is subjected to this load P at a distance h from the bottom, which is generating a bending moment, maximum bending moment of 30 kilonewton meter, will, and it will also be within the limit, that allowable limit will be 15 MPa. That means the beam which you are making of the wood will generate or will create this much only of bending stress, and it will be subjected to the 30 kilonewton meter of the bending moment. Okay, you can you know that how I found this, because I directly found the maximum bending stress. Okay, I have just discussed it, that's why I didn't do it again. What I know that the maximum bending moment occur here, so I am only interested that maximum value, because if I make a section which can resist the maximum bending moment, okay, as you know, the bending moment is varying. Okay, I'll draw the figure here. Okay, so if you say it is actually it is sagging basically. Okay, if I take the axis like that, so if I draw, it will be something like this. Okay, this is the value of P into H. Okay, this is the P into H value. So it is varying. So that's why I want to find what is the maximum value, and I know maximum value will occur at the bottom, and that's how I directly used that formula and found the maximum bending moment, and subsequently went for the calculations. Okay, I hope you guys understood this one. Okay, then we'll go for the next part. Now next part is more interesting, that in that case you have, first of all, it is a aluminum post instead of wooden. We have changed to aluminum. Okay, so with the minimum required, what is the minimum required outer diameter? So we need to find this D2 of the aluminum tube if its wall thickness is to be 1/8 of the outer diameter. So the thickness T of the wall is 1/8 of D2. Okay, and the allowable bending stress in aluminum is 50 MPa, and the allowable stress is 50 MPa. So let's do that. So we'll say let the outer diameter be diameter of tube be D2. Okay, and though we know what is thickness, 1/8 of D2, that is given, and let inner diameter be DI. Okay, DI means D, inner diameter. Okay, so I will draw the cross section. So something like this and something like this. Okay, so this is the neutral axis. About this the bending is acting, same bending moment is acting, no change in bending moment. Okay, only the material and the dimensions are changed. This is yeah, so yeah, and you know what are which diameter. So this one is the outer diameter d2, and this one is the inner diameter di. Okay, so now we know inner thickness is 1 by 8th of d2. So if I find di, so what will be di? Di will be d2 minus 2 times of thickness, correct? Di will be d2 minus 2 times of thickness. So what is d2? D2 is d2, and this is 2 into d2 by 8. That means di is d2 minus d2 by 4. That means di is nothing but 3 by 4 of d2. That means we got di in terms of d2. Now from this, what we know, again we will go for the bending formula. So bending formula, and why I didn't calculated the bending moment here, because bending moment is same, it is not going to change. So that is mb by iz is equals to minus sigma x by y is equals to e by rho. So again we have been given a bending moment that is 30 kilonewton meter. Iz I don't know because the diameter is unknown. Sigma y we know what is the allowable value, 50 MPa, and y we will find what is the y. So sigma allowable aluminium is 50 MPa. That is the allowable bending stress. Now as you can see from this figure also, so this will be the center. So as I told, I will draw this thing radius. So you know that there is no material here, there is no material inside. Nothing is there. That means there will be no stress will be there, no material. So there will be stress will start varying from here, and it will vary till there. And obviously because this point is farthest, this will have the maximum, or if I say this will have the maximum. You don't confuse that this will be maximum, because the y is increasing in this direction. So this will be the maximum. So we know what we have to take for y max. So what will be our y max? Our y max will be this distance here to here, and what is that? This distance is nothing but d2 by 2, half of the diameter, outer diameter. So y max will be d2 by 2. And how to calculate Iz? So Iz will be the same way we calculated the polar moment of inertia for a hollow section. Same way, just by we have by 32, here will be by 64. Rest will be same. So pi by 64 di to the power, I'll not write di, it will be d1 or d2 not 1, d2 power 4 minus d inner power 4. Now we know what is d inner in terms of d2. D inner is 3 by 4. So it will be pi by 64 d to the power 4 minus 3 by 4 d to the power 4. So I will take d to the power 4 outside common. 64 into d to the power 4 to 1 minus 3 by 4 to the power 4. So can someone tell me this value? What is this factor? This factor 1 minus 3 by 4 power 4. 0.3164 into pi by 64 into d to the power 4. So this is our Iz that we have to use. Now we'll plug in everything in our bending formula. So obviously we don't need this part, we need only this part, and obviously I'll skip the negative sign here, because I am interested in the maximum, where the maximum is happening. So again I have 30 kilonewton meters, so 30 into 10 power 6 divided by this 0.3164 pi by 64. Yeah. Okay. I think you have to one minus from that. Okay, 0.6683. Okay, thank you. 0.683, and this is the 2 power 4. Okay, is equals to, we know what is sigma allowable is given us, so 50 MPa, so 50, and what is y max, we know what is the maximum value of y, it is d by 2 or d2 by 2, so it will be d2 by 2. Now from here what we can say, it will be 30 into 10 to the power 6 divided by 50 into 0.683 into pi by 64, or I will say directly pi by 32, so 32 will get multiplied here, pi will be here, and yeah, is equals to d to the power 3. So d2 will be 30. Okay, I'll cancel things, so it will be 3 into 32 into 10 to the power 6 divided by 5 into 0.683 into pi power 1 by 3. So if someone is able to find this, please let me know what is the value of d2. Okay, 207 point something. Okay, so d2 is coming 207.6 mm, so we can safely say that 208 mm. Okay, so we found d2, that is the outer diameter, and we can find inner di, that is 3 by 4 of d2. So just multiply this with 0.75 and tell me what is the answer. 208 multiplied 0.7, 156 mm. Okay, so that will be the di, that is the inner diameter. So we were able to find that inner diameter is 156 and outer diameter is 208 for the aluminum case, where we have allowable stress of 50 MPa and it is subjected to same bending moment of 30 kilonewton meter, and the length of the beam also same. Okay, so you can see that how, if we have, because see there is a difference in material, so you can see when it was wood, so we knew that the allowable is less. Okay, it was around 15 only. Okay, so the diameter required was around 273, 274. Okay, now as soon as we change it to aluminum, and what we did, we increased our allowable value, because the aluminum can allow more bending stress, so our diameter also reduced to 208, some 50 60 value it got reduced. Okay, so that is how we choose what material to be used to make some beam. Okay, because we have to see by which material, by utilizing minimum material, we can get the maximum output, because we have to optimize the weight also. Okay, right now we are not talking about the weight, but when we come to a real design situation, suppose we have to design a shaft which is subjected to bending, or suppose we have to design some beam which is subjected to bending somewhere. So in that scenario, weight also plays a very important role. Right now we are not so, as because our as we will go for a heavier material, or a material having higher density or longer beams, so weight will also increase, the self weight of the beam that we call. So for that part we have to think of best material, so that we can get maximum strength with minimum weight. Okay, and that's how the steel plays a very important role. So because it's a very high, having a very high value of strength to weight ratio. Okay, it has a very good strength compared to its weight. So that's why where it qualifies for all the important engineering applications. Steel. Okay, so this was one of the design question. Okay, now let's move to another problem, last problem for today's session. So in this problem, and it's quite interesting, and I hope you guys might have seen some problems like this, but this problem is somewhat related to the concepts which the professor told in the first lecture, where he translated the force and how while translating how the couples are generated. So where he was telling that concept. So in that I have chosen this problem from that only. So how we can translate the force from one place to another and how we can form the couple. He showed that in the first lecture. I hope you guys remember. So it is quite interesting, this problem, and we'll see how we can solve such problems. Okay. Now this is also a design problem, because here we have to design the dimensions. Okay. So this problem says a fiberglass bracket ABCD. This is a glass bracket is there, ABCD. It's made of fiberglass of a solid circular cross section. Okay. So the cross section is solid and it's circular, has a shape and dimensions as shown in the figure. So it's having some this shape, a bracket shape, and dimensions are mentioned here. A vertical load of 40 Newton. So this P 40 Newton acts at the free end D. So at this end a vertical load acts. Okay. Now determine the minimum permissible diameter of the bracket. So it is asking us to determine what is the minimum permissible diameter if the allowable bending stress in the material is 30 MPa. Okay, the allowable bending stress in the material is 30 MPa and B is given as 37 mm. Disregard the weight of the bracket. So we are not concerned right now what is the weight of the bracket or what is the moment generated from the weight of the bracket. We are only worrying about what is the this moment, this load which is acting 40 Newton. So like how much diameter we should make so that the material bending, allowable bending stress in the material should not exceed 30 MPa. Okay, so what I'll do, I'll copy this figure and then we can see how we have to solve this one. Okay, so this is for us. Okay, so first of all, in this problem or in this kind of problem where you can't really find what is happening or where is the bending moment coming. So first of all, in this kind of figure we have to draw the bending free body diagram. We have to use some concepts of mechanics and we have to come up with a free body diagram. Then only we can understand what is happening. Okay, so what I will do, of each of these parts A, B, B, C and CD, I will draw the free body diagram, and because I have a luxury to go from anywhere. Okay, it's not like fixed that I have to go from this side, from A, okay, or B I have to start. I have the luxury, I can start anywhere, but the most important part is that the the body should be in equilibrium. It should not go out of equilibrium. It should remain in equilibrium. Okay, so that is the most important part. So what I will do, I will start with DN. Okay, because already the force is given there, the load is given there. Okay, so I will draw first for DC. So I will say FBD, free body diagram, we will draw for DC. Okay, so what I will do, I will draw the DC part, DC part here. Okay, don't get confused that it is rectangular cross section. Okay, it is circular only. Okay, I am just not drawing it in that sense, or I can draw like this. So you will remember that it's circular, it's not rectangular. Okay, and this is end D, this is end C, and I am drawing it. You know this, I have explained this. When we draw free body diagram, we draw very small distance away from the joint. Okay, from that place where it is joint. Okay, to reveal the force, reaction forces. Okay, so this P is given here. P is given here. Okay, So first of all, if I have to translate this force, how I will going to translate that? So what I will do, I'll draw one force here P like this. Okay, I'll draw force here P like this. So what I have drawn, a similar force I have drawn here P acting in same vertical, and I have drawn another force P which is acting in the vertically downward direction. Now because I have added this here, you can understand nothing has been changed as I add this, because the same force which is acting upward and same force which is acting downward has been added, so it doesn't change much. But what happens, you can see there is a force which is showing like this, okay, which is having a couple. You can see the forces are in opposite directions and they are separated by a distance. That means it is causing a couple. That means how it will come? It will come something like this. So I have translated this force to here. So now what I have resultant is, I have got a P here and there is a couple. How is that couple? So the couple is something like this. This couple is causing a bending. Okay, something like this. This is a one way to do this. Okay, another way you can assume is simple as that this is a cantilever, because this part is acting. If you look just only this part, so this part will just act like a cantilever. So you are applying a load and it will bend. So it's just like a cantilever. Okay, so in a similar sense, I have shown you how this will vary. So basically the bending moment will be maximum here. You know that even in the cantilever the bending moment will vary, so it will be maximum here, and that's how I got a maximum value of bending moment here. I am just drawing the maximum value. Okay, so I am drawing at these places which are prominent to me. Okay, so I have a load, I translated that load here and I got a maximum bending moment, which is what, this P will be multiplied with this distance. So distance is given 2b, so it will be 2pb. Okay, now what happened, this joint, at this joint the bending moment as well as the forces will be just translated to this vertical CB. Okay, so what I will do, draw ABD for CB. Okay, so I will draw FBD for CB. So how I will draw that? So let's draw first CB part. So it will be something like this. Okay. Sorry. Okay. So you can see that this force, mention this is G, this is C. Okay, so this force which is acting upwards with the magnitude of P at C end, and I'll write the C here also. This is C, this is B. Okay, so this force which is acting upwards with a magnitude P, so to have the joint C, this full joint C in equilibrium, okay, in the part BC at C again there will be a force, but it will be in the opposite direction of this one. So there will be a force, but it will be in opposite direction. Okay, so how it will be? It will be like this, vertically downwards. Then only there will be an equilibrium at that point. Okay, this is just simply coming from equilibrium. Okay. Okay, and now similarly we have a moment. What is the moment? 2 into PB, and how it is coming clockwise. So to have equilibrium, moment equilibrium at that joint C, to counter this clockwise movement, what will be there? There will be an anti-clockwise movement with same magnitude as this movement at C, that is 2pb. So value will be same, but it will be in an anti-clockwise fashion, and this 2pb, sorry, 2pb, it will be in the opposite sense. Okay, so now you know what is happening in CB at end C. Okay, so to satisfy, again we have to apply the equilibrium equation. So we have three equilibrium equation. What I am doing all the way, I am applying equilibrium equation only. So again we have to apply the equilibrium equation in this part. Okay, so when there is an axial force here, so obviously to counter this there should be an axial force here also. Okay, that means there should be an axial force here to counter that. Okay, and to counter this movement which is there. Okay, so now I have satisfied the equilibrium in this direction, means force equilibrium along this is satisfied. The force equilibrium along this, there is no force in the horizontal direction, so no need, nothing has to be done. Now coming the part to the movement. So there is a movement here which is in anti-clockwise direction at this end. So at this end, to make this part BC in equilibrium also, what I have to do, I should have a clockwise movement like this to counter that movement. So what I will do, I will get a clockwise movement like this, 2pb, a clockwise movement here. Okay, so this we got the free body diagram for CB. Now we'll do for free body diagram for AB. Now that is the last part. You can see from the figure, we have done with this, we have done with this. Now only the last part is there, this part. Okay, AB. Okay, so I'll draw the AB. Yes, sir. Okay, this is A, this is B, and this length is 6B. Okay, now to have equilibrium at joint this B, so I should have a equilibrium at joint B. So whatever forces are acting at joint B will be transmitted to the joint B of AB. Okay, similar but in the opposite sense. So this load is vertically here, vertical upward P. So it will come how? It will come vertically downward. Okay, opposite sense. Okay, this movement is how? This movement is 2pb, and how it is acting? It is acting in a clockwise sense. So what will be the movement acting there at B? In AB it will be anti-clockwise, 2pb. Okay, it will be anti-clockwise to counter the one at the B end of BC. So now we got this. Now we know that end A is fixed. You can see it is a fixed end. Okay, so now we can find what is the value of end A. If we want, we can find what is the value of end A. How we will find? First of all, we have to satisfy the force equilibrium. So is there any force in horizontal direction? No force. So no force is required to equilibrate it. Is there any force in the vertical direction? Yes, there is a force which is acting vertically downward here. So I need what? I need a force which is acting vertically upward there. Okay, so I'll draw vertical this force P. So now the AB part is in equilibrium, force equilibrium. Force equilibrium is satisfied in horizontal and vertical direction. Now coming to the moment. So what I do, I come at this point A and I find what is the total moment acting. So you can see total moment is the moment due to this 2pb and the moment caused by this vertical force. Okay, so what it will be? It will be I'll take any one of the as positive and negative, or you can go with the convention also. Okay, so we know that if on, as I just now told, on the left of the section this clockwise will be termed as positive bending moment, and on the left of the section if there is an anti-clockwise it is termed as negative. Okay, so what I will say, or in the same sense, if we go to right, so anti-clockwise is termed as positive and clockwise is termed as negative. So that I'll do, I'll say let's find what is the total moment about point A. Okay, so moment about point A, it will be 2pb. 2pb is positive because it is clockwise and anti-clockwise, minus, why minus? Because this is going to be clockwise, so minus 6pb, that will be giving me minus 4pb. Okay, minus 4pb, that means I have to put a minus 4pb. So on the left of the section it should be anti-clockwise, not clockwise. So it will be like this, 4pb. So this will be the bending moment acting at the end A. Okay, this will be the bending moment at the end A. Now we have drawn the free body diagram of each of the part. Okay, now we can draw the bending moment because we are interested in maximum bending moment. You understand why we are doing this? Because what the question asks us, so question asks, it asks determine the minimum permissible diameter of the bracket if the allowable bending stress in the material is 30 MPa and B is given as this. So first of all, what we need to find where the maximum bending moment is coming. Okay, in which part it is coming. Okay, so you can see that in this part you are getting 2 pb, and this 2 pb is coming due to this cantilever action of DC. Okay, so it is 2 pb. That is not that is one thing. Okay, so I will say here maximum bending moment in DC is 2 pb. That is the maximum. I am not just worrying about the sign right now. Okay, I am just worrying about what is the maximum magnitude. Now coming to the other part, that CB. So if you look at CB, this P load is just nothing but it's an axial load. Okay, it is just an axial load. Okay, but we are having this bending moment, which is what 2 pb. So this is only there, and it is where it is means it is same throughout. Okay, this will remain same, it won't change. Here there will be a variation of bending moment. Okay, so I will draw also that. So if I draw it, it will be like something this. Here it will be maximum 2 pb, like this. Okay, in this case it will remain constant. The bending moment remains constant. It will be same, 2 pb. Here also 2 pb. Okay, so you can say that this part is kind of like subjected to pure bending, this part. Now coming to the CB, AB part. Okay, so you can see the bending moment at this end is 2 pb. Okay, here it is 2 pb at end B. Okay, and that is positive. Okay, so what I'll do, I'll put a positive bending moment, and its magnitude will be 2 pb. 2 pb. And what happens after that, this P load is applied, so which will take it to a negative value. So what it will happen, it will go negative value of here minus 4 pb. It's going a negative value, and somewhere like this it will intersect, something like this. It will be 0 somewhere in between, and it will vary something like this. Okay, it will vary something like this. That means from this whole we understand that maximum bending moment is coming at A, which is 4 pb. That is the maximum value. So maximum is at A, and its value is M max 4 pb. Okay, that is the maximum value. Okay, so yeah, that is the maximum value. So then we got the maximum value, and we know what is P, what is B. So 4 P is I think 40 Newton given in the question. P is 40 Newton and B is 37 mm. Okay, so I'll keep that value here, 40 Newton and 37 mm. So it will be 160 into 37 Newton mm. Okay, so this is the value of this. Now it is asking, so now we know in what is the maximum value of the bending moment. Okay, it doesn't matter in which part, because the whole bracket is made of same diameter. Okay, diameter is not varying anywhere. Okay, the whole bracket is made of same diameter, so I am not worrying with that. The only problem was I need to find where the maximum bending moment is occurring, and I found this. Okay, now what I need to do, I need to see how I need to visualize the diameter. So I'll draw the cross section. So it is a solid. In the question itself it is given, it's a solid fiberglass rod. Okay, so this is the center. Obviously I am interested in maximum, so here only it will be the maximum. Okay, and suppose the D is the diameter, so this will be D by 2. Okay, D is the diameter, suppose. So this point will occur at D by 2. So what I will do, I know, that means what I know y max. Y max where it will occur is d by 2. I know Iz is pi by 64 d to the power 4. I know moment m max is 160 into 37 Newton mm. Okay. Now let's apply the bending formula again. So what is our bending formula? I know one more thing, that is sigma allowable. So I know sigma allowable fiberglass Fg, I'm writing. So sigma allowable given as 30 MPa. Okay, it's given as 30 MPa. Yeah, so it is 30 MPa. Okay, so what is our bending formula? It is max by Iz is equals to minus of, I'll drop the minus sign right now because I'm not interested in the way compression or tension. I am interested in the maximum value, so sigma x by y. Okay, so m max is what? 160 into 37 Newton mm divided by Iz is pi by 64 d to the power 4 is equals to 30 MPa divided by d by 2. Okay, y max is d by 2. We know what is y max. Y max is d by 2. Okay, so from here 160 into 37 into 32 divided by pi into 30 is equals to d power, and 1 I'll just write directly. So cube root of this will give us d. 160 into 37 into 32 divided by pi into 30 cube root of this will give the d. So if anyone can find this value, $12.62. Okay, just check once more whether value is correct. I thought it will come somewhere around less than little 12. Just check once if possible. Okay, yeah, cube root, it's a cube. Okay, no issue. Yeah, so that is the diameter we got for fiberglass. Okay, so this is the diameter we get for the fiberglass, because here most important point is to find the maximum bending moment. So where it occurs, so it will occur in this case at A. Okay, and how we come up with that, we just need to draw the free body diagram, and we keep on drawing the bending moment diagram basically. Okay, so when we draw the free body diagram, we can also draw the bending moment diagram, and from that we can understand where it will be varying how. Okay, yeah. Yeah. Okay, one thing, I think this won't be like this. I think I drew it in a wrong sense, because there you can see that there are two different signs. Okay, the bending moment having two different signs. I just ignored, I think, this part. So you can see I considered them same. So you are having two different signs. So you have to make sure that you are doing correctly. Okay, so this is causing a movement like this, and this is causing a similarly a movement like this, and you have to consider that there is no force here. Okay, if there would have been a force like this, then the situation would have been different, like we have in the part AB. Okay, because then you have a variation like this, that force will cause a variation. Okay, but that is not the case here. So means I will draw with the sign convention. So if we see, if we assume this as the axis of this beam, and if we consider the positive and negatives, so if you can see that this will be actually sagging, because it will this movement and this movement will cause a compression in this top surface and tension in this part. So basically I can draw this as positive. So I drew it correctly, but I wanted to show it with the proper sign. So this will be positives and the other one will be positive, like this. So because there is no P acting there, this load in this way, there will not be any variation as we have in AB. Otherwise there would have been a variation, and also because this uniaxial load will not cause bending moment. Okay, this P will not cause bending moment. Okay, only lateral load causes bending moment. Okay, so here here this is a lateral load, so it causes bending moment. Here this is the lateral load, it causes bending moment. Okay, axial load won't cause bending moment. Okay, so I think you guys understood this part, this problem. Here the main, yeah. So yeah, here the what I found, the catch is important in drawing the bending moment diagram. Okay, or finding where the maximum bending will occur, and for that we should have the knowledge of drawing the free body diagram. Once we know how to draw the free body diagram, then it is going to be fine. Okay, so that is the catch. Yeah. Okay, so there will be more such problems where, like, different scenarios where beams are used. So this is one of the examples. So this bracket can be used for any kind of like you can put a load here. We generally see these brackets in our homes. Okay, so they take some load. So we generally see that they are made of polycarbonate or some polyethylene material kind of things. Okay, so they are designed in a fashion specific for the specific load. So how much bending they can resist, and for that the load is also designed. So sometime what happens that load will be given. Okay, so you will be given that for a particular load how much diameter we need. So the way we did just now, so we have been given a load, so that this much load will come, and design how much will be the diameter, with minimum diameter we can go. Okay, sometime what happens that we will have a restriction with the diameter. So the diameter will be, there will be a specified maximum diameter that we can't go beyond this diameter. That is a specified diameter. Okay, so somewhere this will be acting as a pin. This bar will be acting as a pin, and it will be inserted somewhere in some parts, and the diameter of the part or the hole which we can make in a part will be of specific size. We can't go beyond that, because as you have seen, when we make a hole in a plate, you have seen when it is subjected to plane stress, it causes stress razors near the edges. There is stress concentration near the edges. So there are many factors which are there involved. So because of that, there could be a restriction on the diameter also. So in that scenario, we will already know the diameter, and then we have to come up what is the force. So we have to come up how much load we can put at this end, okay, or how much bending we can generate at this end for that given diameter. So we can find the load. Okay, so that could be a kind of analysis problem. So that is also there. So which is, but it always comes from the perspective from which we are going. Okay, whether it is a design perspective or whether it is a perspective where we have been given some design, but we need to find whether this can work or not. Okay, so suppose in a problem I say that this diameter of the tube can be maximum to 15 mm. So for that 15 mm you find the load, maximum load which can act. So again we have to know what is the maximum bending moment From there we find what is that bending moment, and then we come up with the with this value of P in the same fashion. Okay. Yeah. Yeah. So any doubt in this one or other questions which we solved today? Yeah. Yeah. Thank you, Arjun. Yeah. Yeah. Thank you. Thank you. I always look forward to this class because we have a live discussion and you guys ask questions, so that motivates me also, like to try to put it in a better sense, so that you can understand, because you hardly find any other way to like be in touch with the professor, or you put your questions through groups, through announcement, this thing. But okay, that is passive way of doing it. I feel this is more active way for learning. Yeah. 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 Sure. 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 Yeah. Sure. 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 Yeah. Thank you. Thank you. Thank you. Yeah. So we'll close for today. Thanks for yeah. Thanks for joining. Thank you very much. We'll close for today. Yeah. Thank you, Lokesh. Thank you for coming. Thank you.